All right, so what have we been talking about recently?
Kinetic and potential energy.
Yeah, kinetic energy, potential energy, sort of just energies in general. And what did we say happens to something if it's right here? What kind of energy does it have? What happens when I drop it? Kinetic. Okay, so it transfers, right? It goes from being potential energy to being kinetic energy. Okay, and that goes hand in hand with the fact that energy cannot be created or destroyed, okay? What can it do? Huh?
Converted.
Yeah, you can transfer sort of kinds of energies back and forth. So you can go from potential to kinetic, from kinetic to potential. There's other kinds, but we're not going to worry about those today, all right? We are going to worry about just going from potential to kinetic. And if energy cannot be created or destroyed, that means today we're going to say that total energy of an object is equal to its potential energy plus its kinetic energy, okay? And this is something that we call an ideal system. In an ideal system, we have the absence of something. There is no, what do you think it starts with an F?
Friction.
There's no friction present in an ideal system. So during any problem we're doing today, do you have to worry about friction? No, we're going to ignore it. Acts like it doesn't exist, okay? All right. So let's start by thinking about this ruler, okay? Right now it has potential energy, right? And when I drop it, it changes to kinetic. And then what happens to its potential energy when it's on the ground? Okay, let's see. So if I asked you to figure out if we have some ruler of mass m, and we're starting it from some height h, and I want to know what its final velocity is when it reaches the ground. Okay, so we're going to go through this together, all right? Now, total energy is potential energy plus kinetic, right? So what we're going to want to do is we're going to say that the potential energy that it starts with, so initial potential energy, plus the kinetic energy that it starts with is going to be equal to however much potential energy it ends with, plus however much kinetic energy it ends with, okay? So this is basically just restating this up here. Because however much energy we have right here, how much energy do we have to have over here? The same amount, right? Okay. Now, what is the equation for potential energy? This is just gravitational. We're not dealing with springs right now. mgh, right? Okay. And then what is it for kinetic energy?
1/2 mv squared.
And then once again for potential energy? mgh, right? And then another 1/2 mvf squared. Okay. So yes, Rose.
What's the mhvf?
What's the what?
So
Okay, it has some mass m, some height h that it's getting dropped from, and we're trying to find what its final velocity is.
Oh.
We're not using numbers. We're just using variables. That's okay. So remember when we did kinematics, I always said to get rid of what's zero first, right? Okay, so what is zero up here? What's going to be equal to zero? Which knot? The potential or kinetic energy. Which one's going to be zero at the beginning? Why? Yeah, it's not moving yet, so we're going to say bye. Okay, which one's going to be zero next? The final potential energy or the final kinetic energy? Why is the final potential going to be zero? Because it's on the what? Ground. And we call ground zero. Okay. So now we have that mgh is equal to 1/2 m vf squared. And we want vf alone. Bless you. So how are we going to get vf by itself? What are we going to do? Okay, so we're going to multiply by 2. We're going to have 2 mgh equals mvf squared. Then what are we going to want to do?
Right.
When we divide by m, what happens?
The m's cancel out.
Yeah, the m's are going to cancel out and go away. So we're going to have 2gh equals vf squared. So what's our final step here?
It's square root.
Square root. Oh, you got to put that 2 in there. That's 2gh. I forgot my 2. I had to squeeze it in. So does how we went through this and moved around with the algebra make sense to everybody?
Yes.
Awesome. That means that once I see you stop writing, that we're ready for our first example together. So does anybody here, is anybody a baseball player? No? We have one. Okay. You'll, I guess, appreciate it. But I was watching a documentary the other night, right? I like to watch them with dinner. And there's this one on Netflix. I can't remember what it's called, which is really sad, but you'll be able to find it pretty easily. There's this guy, right, who he got charged for murdering a girl. And he was given the death sentence, okay? He was exonerated, though. Do you guys know what exonerated means?
Like, they removed all of the charges.
Yeah, they removed all the charges and let him free. How he was exonerated was there's this HBO show called Curb Your Enthusiasm. Have any of you guys heard of it?
I've seen this.
Wasn't it good?
It's so funny. Well, like, it wasn't funny because that was like a struggle. But it was funny. It was funny about how they proved that he was innocent.
Yeah, there was footage of him from that HBO show of like him being at a baseball game. Because they had gone there to film it because Larry David really wanted like an actual Dodgers game. And they caught clips of him going back to his seat with his daughter in the footage, which is crazy. Anyways, that made me feel like I wanted to go to a baseball game. So this problem's about baseball games, okay? Catching a home run. You guys always have some stupid reason behind the problem I do. You know that. All right. So let's start by knowing that we're going to need to list down our knowns. Just go ahead and make the column, okay? So we're in the bottom of the 9th inning, and a player hits a baseball over the outfield fence, okay? The mass of the baseball is 0.15 kilograms, all right? And the ball is going to leave the bat with a speed of V naught equals 36 meters per second. Okay? And a fan in the bleachers is going to catch it when it's at a height 7.2 meters above where it was hit. We want to know 2 things. We want to know the final kinetic energy of the ball right before it's caught, and we want to know how fast it was going right before it was caught. And we're going to draw a quick little picture to help you see this, okay? This is the ball right here, and it's leaving the bat, all right? And it's going to fly, and this is where it's going to get caught by the person in the bleachers. So when it's thrown, we're going to consider that as its height is equal to 0 meters, okay? And when it's caught, the height is equal to 7.2 meters. Okay, just to give us an idea of where we're starting from. We're going to make where we start from 0 to make our math a lot easier on ourselves, okay? Does everybody have this down?
Yes.
Okay, so let's return to that equation we were just doing. That the initial potential energy plus the initial kinetic energy is equal to what?
The potential final kinetic
Mm-hmm. Okay. What can we get rid of? What's equal to 0? I'm hearing literally every single answer. Okay, is this one going to be 0? Yes. You guys, what's the initial height?
0.
0. So what do you do when you do mass times gravity times 0? 0. Is this going to be 0? No, because how fast is it going?
36.
Is this going to be 0? No. Is this going to be 0? No. No, because it's going some speed when it reaches the hand.
Right.
It doesn't just stop randomly. Also, we're asked to find that speed, and we're asked to find that kinetic energy. Why would I ask you to find stuff that was both zero? Okay, so let's write this in terms of our equation. We're going to have 1/2 m v naught squared equals mgh plus 1/2 m vf squared. Okay, what are we asked to find in part A? Okay, is this the final kinetic energy? Is this? Is this?
Yes.
Okay, so we want this whole term, right? Not just one variable from it? Right, okay. How do we get this entire term by itself? Yeah, exactly. We're going to say 1/2 m v naught squared minus what? mgh. And it's all going to equal out to that final kinetic energy. Now, before we solve for this, do we need to rearrange anything else? No? Okay, so show me. Get the answer for me. What's it going to be? What is our final kinetic energy going to be? Because all you got to do is plug it in now. Let me know when you think you got the answer. Yes.
86.6.
Which is 86.6 what?
2.
And what are the units? Joules. Good job. Okay. So that's our answer to part A, right? Right? Okay. Cool. So now to go into part B, what are we asked to find? That final velocity. So you know what's really cool?
Wait, what? You just have to say 9.8. Yeah, the G stands for gravity.
Yeah, the G is the acceleration due to gravity, you guys. Remember that?
Mm-hmm.
So to find part B, we're going to take that kinetic energy we just found,
All right.
and we're going to equal it to this, because that's what it equals, right? So I ask you, how do we get VF alone? Okay, so we're going to multiply by 2. So we're going to have 2 times 86.62 joules equals mv squared. What do I do next? And what's our mass? And then what'd you say?
Square root.
Yeah, then we're going to square root it. Tell me what you get. Yeah.
How do you plug in the equation to get 86.62?
So like, how do you do the parentheses for this?
Yeah.
Okay, so for this, what I would do personally, okay, is I would put one big parenthesis, okay? Then I would put 1/2 within its own. I put m in its own. And then I put the v naught and the squared in its own, and then close it off. And then I put minus, big parentheses, m, g, h.
Okay.
The more parentheses, the better. Covers your back, keeps you safe.
Whoa.
Whoa, that's
What'd you get?
33.98 or
33.98. What are the units?
meter per second.
Meters per second. Beautiful.
You would take 34, right?
Yeah, I guess.
Because technically it's the start of the nine.
Do you guys have any questions about this one? You sure? Promise?
I promise.
Pinky promise?
Sure, no.
No?
I mean, I'm good now, but I'm not saying it's
So I want you guys to think about something while I erase this, okay? I want you to think about if this ball had more mass, okay? It's hit at the same initial speed, it goes the same height, everything else is the same, only the mass is changing. When it hits that person's hand, is it going to be going faster, slower, or the same speed? Don't say anything until I'm done erasing. Okay. So, we're doing the same thing, right? We're hitting a ball. It's going to go the same height, and it's going to be hit at the same starting speed. However, the ball weighs more. It has more mass. When it hits the person's hand in the stands, is it going to be going faster, slower, or the same speed? Raise your hand if you think it's faster. Raise your hand if you think it's slower. Raise your hand if you think it's the same speed. Raise your hand if you refuse to raise your hand. Awesome, it's the same speed.
I didn't remember too.
Oh, nothing changed except the math?
That's not a trick question, it's physics.
I just did the math, I put 0.20 in instead.
Think about that. Think about why it's the same, and we're going to move on, okay? Now, does anybody in here play tennis? Oh my gosh, I got 1 for 1 on each of these. Woo, score. Okay, so this one's going to be about tennis. And it makes sense that you're a tennis player because you're also a runner, right? There's a lot of running in tennis. I found that out. My husband plays tennis, and he's been trying to teach me for a long time. It's not been successful so far. The running, I'm okay on. The making sure I actually hit the ball, it's real rough. It's real rough. Okay, so we have a tennis match, okay? And a player is going to win a point by hitting the ball, which has a mass, remember, write out your knowns, has a mass of 0.059 kilograms, okay? And what's going to happen is the ball's going to hit the ground, okay? And when it hits the ground, it's going to bounce upwards with a velocity of 16 meters per second, okay? And that's when it's on the ground, so it's coming from the ground up. Then we have another lucky fan who's going to catch the ball, okay? And when they catch it, it's going to be going 12 meters per second. All right, I want to know how high above from where the ball bounced the fan is. So this is what's happening. It's on the ground, it hits the ground, bounces up, and it gets into somebody's hands. So what's our original height going to be? 0. And we're trying to figure out what the heck this one is, okay? So once again, we're going to want to say that our initial potential energy plus our initial kinetic energy is equal to that final potential energy plus that final kinetic energy. What up here is going to be 0? The initial what? The initial potential. Anything else? No, nothing else. Okay. So for this one, we're going to say 1/2 m v naught squared equals mgh plus 1/2 m vf squared. Okay? And remind me, what are we looking for? Yeah, we're trying to find this h. What's our first step? Yeah, we're going to subtract that from both sides, right? So we're going to have 1/2 m v naught squared minus 1/2 m vf squared is equal to mgh. What do we want to do now? Yeah, we're going to divide by mg. Good job. Do we have to do anything else? No, we're just going to plug it in. Let me know when you think you have an answer. Good job. You're on a roll today.
So fast.
Yeah, it's only today.
He said on
It's not only today.
Don't get used to it.
You have sprinkled days of where you're just like really on top of it. I feel like it's actually every day, but you just don't show it every day.
What does she get?
5.71 meters.
That was a lot to do. Calculator.
It is a lot to type in, isn't it? That's why you got to be careful with those parentheses. It's stressful, right? Do you guys have any questions about this one?
I have no.
Okay, if you didn't get that answer, you typed it in your calculator wrong.
Please no, I'm still trying to teach, and I'm like,
That's why you guys listen up, because I know stuff's hard to type in your calculators. That's why when you're doing problems, you should always write out this and then write it out with all of the numbers in it.
That's what
Because if I see that and that you did all of that right, but just got the wrong number, you will get most of the credit for the question. Because I'll know it's just a calculator error, not a you not understanding physics error. Okay? Can I erase this? So maybe this one will get a few more hands. Who's been to a water park? Okay, that one's a lot more relatable, it seems like. Cool. Who's gone down a slide at a water park? Awesome. Okay, so we're at a water park now, okay? And we've got 2 slides. Slide 1, just go straight down, all right? So you're starting down up here. You're ready for a fun time. And then you go into the water, right? I'm just going to draw some splashes. That's a really bad splash. Okay. Then there's the other one. And what it does is it goes down, but then it sort of goes straight. So it slopes and then it levels off. Now, even though I didn't do a very good job drawing these like very similar sizes, this height, don't judge my, I'm not an artist. These heights are the same, okay? I know I didn't draw it to scale very well, but they are. So this one, so if this is 5, this is 5. If this is 2,000, this is 2,000. All right, you guys? Sound good? Okay. Now, you are the person on both of these, which means the masses are the same too. And what do you think your starting velocity is? 0, okay, in both scenarios. So, my question for you, are you going faster when you hit the water in case 1 or in case 2, or are you going the same speed for both of them? Okay, if you think, hold on, if you think you're going slower in case 2, raise your hand. If you think you're going faster, raise your hand. If you think you're going the same, raise your hand. You're going the same. Because they're both the same height.
That's true. I was looking at the slide when you were,
Yeah, I was looking at how it.
Okay, think about it. Think about it, think about it, think about it, okay? So if we say the initial potential energy plus the initial kinetic energy is equal to the final potential energy plus the final kinetic energy, for both cases, what is the initial potential energy? No, it's not.
Oh, wait.
What's the initial kinetic energy, though?
0.
What's the final potential? 0. Okay, so that means that whatever our initial potential energy is, that our kinetic energy has to be the same, right? Our final one? So mgh is equal to 1/2 mvf squared. Your masses are the same. Your starting heights were the same. You're on Earth for both of them, right? So doesn't your final velocity have to be the same? Yeah. Math doesn't lie. Sometimes you can have differing opinions in like lit, not in physics. Well, that hurts physics feelings. All right, let's keep going, you guys. So, we started out at the same initial speed in both of those situations, right? Okay, now we're going to do an example where we don't start at the same speed. And we're actually going to do the math for it, okay? Even though we technically did the math for that one too. Who's been snowboarding?
Oh, I did.
Nope.
I got 2, I'll take it. Okay. So, we are snowboarding, okay? And there's 2 scenarios. Here in case 1, you're snowboarding. You've got a little helmet. Keep yourself safe. Got some cool goggles, okay? And you're going at an initial speed of 4 meters per second, okay? And you're going to sort of go up this hill. And when you get to the top, just leave it alone. Let them do their thing, okay? Once you get to the top, you're going to have a final speed of 0 meters per second, okay? You're going to have slowed down as you've gone up. Then you decide, I'm going to go up this same hill, but I'm going to try it faster because I'm brave. Okay? And you start out at the absolutely amazingly shocking velocity of 5 meters per second. All right? And we sort of want to know how fast you're going when you get to the top. Like, what's going on up here? Who knows, okay? So don't worry, I've got a little bit more information for you to get through this problem, all right? But this is the base work of our picture, okay? Does this picture make sense to everybody? It's the same hill, so they're both the same height, all right? Now, our knowns. Other than what we have over here, we have a mass of 75 kilograms, okay? And, well, that's all we really know. Yeah. We know these velocities and we know that mass. That's it. And we want to know what this final speed is. So, you know what I think would be a really good idea?
Cross out height.
We're just not going to worry about height.
Yeah, we're not.
No, we don't need to. Height doesn't matter. The only thing that matters here is what? Yeah, which is what kind of energy? Kinetic. We only care about kinetic. So how about we find the kinetic energy for case 1? How are we going to find that? We're going to do 1/2 times what?
75.
75 times what? 4. The top case. Yeah. Okay. Tell me your initial kinetic energy in this case 1. When you start out, how much kinetic energy do you have? Enough is not the answer. Yes, it is 600 joules. Good job. Okay. How much kinetic energy do you have at the start of case 2? Where you're going 5 meters per second instead of 4.
937.4.
Okay, so listen up. What do we know is our kinetic energy right here? At the top of this first case. It's 0, right? So from here to here, how much kinetic energy do you lose? 600, okay. So if we know that from point A to point B, you're going to lose 600 joules of energy, can't we know the difference between these? If we get the difference, won't it give us what the kinetic energy will be here? I mean, you're right. So let me tell you what Randy did. He said 937.5 minus 600. And he did it in his head because he's really smart. And he got 337.5 joules, okay? That's what he did. So that means that right here at the top of this one, the kinetic energy is 337.5 joules, okay? Capiche? Sure.
Wait, hold on. Don't erase anything.
I'm not erasing anything. We're not done yet.
Okay, so
So, if this is our final kinetic energy, what were we asked to find? So can't we say that 337.5 joules is equal to 1/2 mVf squared?
Yes, you can say that if you want to.
So how do we solve for VF?
You gotta multiply by 2 and divide by m and take the square root. There you go.
Multiply by 2, divide by m, take the square root. So what do we get? Yep, 3 what?
Meters per second.
I lost you when you subtracted those two things, and why did you like equal it to the other equation?
Okay, so what happened was, you guys please be quiet so I can explain. Was we said that right here we have 600 joules of kinetic energy, right? That's what we solved for, okay? And then we said we know that when we get to the top, we have none because the final velocity is 0. And then we said that down here, if you solve for its initial kinetic energy, it's 937.5. Due to this problem right here, we know that over the course of starting from here and getting to the top, we are going to lose a total of 600 joules, okay? Because you see how it goes from 600 to nada?
Yes.
So we lost 600 joules, right?
Okay.
It got converted to potential energy?
Yes.
Yes, okay. So we know that from here to here, since it's the same hill, we will have lost the exact same amount of of kinetic energy, right? We'll have lost 600 joules. So to find the kinetic energy of case 2 on top of the hill, we need to take our initial kinetic energy for case 2 and subtract how much we know we're going to lose. And when we do that, it tells us that while we're at the top of this hill, since we started out at 5 meters per second, instead of having 0 joules of kinetic energy left, we will still be moving and we'll have this much kinetic energy left. Because we are moving faster, yep. So then, since we know for a fact that that's our final kinetic energy there, we can set it equal to the equation for final kinetic energy in order to solve for velocity. Does that make sense to everybody? I know it's new stuff. New stuff takes a little while to set in, doesn't it?